So the question is, a molecule contains the following symmetry operations. The given operations are E, 2C6, 2C3, C2, 3 sigma D and 3 sigma V. And the question is, how many classes and order of this point group is. So first of all, what order is? Now order of a group, which is denoted by H, is the total number of symmetry operations that belong to that particular group. So total number of symmetry operations means that it represents the number of ways in which the molecule or the object which is in concern, which can be transformed while it remains indistinguishable from the original state. So even after performing that operation, the molecule should remain indistinguishable from the original configuration. So the configuration should not be changed. So that defines a symmetry operation, and the total number of such operations is called the order. So now the order can range from 1 to many, like 12, 24, 48, to it can be of any number. So range from 1. 1 will be the order for object having only identity element as symmetry operation. For objects with no symmetry or only E to several dozens. And so on. Now, class of a group which is denoted by K now class is the class is the number of distinct set of symmetry operations within a point group. for this molecule, now class is number of distinct set of symmetry operation. So here the distinct sets of symmetry operation is E, C6, C3, C2, sigma D and sigma V. So for this point group, class is equals to 6 and number of symmetry operation is, so we have C6, 2 C6. So it is 1, 2 into 1, 2 into 1, then again for C2 it is 1, 3 sigma D and 3 sigma V. So order is 1 plus 2 plus 1 plus 3 plus 3. So 6 plus 4, 10, 11, 12. It is 12. So this, for this point group, the classes are 6 and the order is 12. So answer should be C. A symmetry point group of 1,3-dichloroalene. So let me draw a, so this is the plane in which this C double bond C double bond C is there. Now from this plane H is coming outwards. And Cl is going downwards. So this is this kind of system. I can show you this. In cyclic, this is kind of this. It is this kind of molecule. So two bonds are in one plane and this two side is on in another plane. Okay. So you see the C2 axis here. So this is the C2 axis. Okay. So our this system 1,3-dichloroalene is similar to that one, and we have the C2 axis passing through here. So the point group of this is C2. Now S4. How is the other one? Now the other one is D2D and S4. Let me show you how D2D looks like. proper allele which is symmetrical. All the bonds are symmetrical. Now D2D will be C2 rotation. This is the C2 rotation along the double bond plane. Okay, so can you see this? And we have a C2 dash. Let me show you one. So this is C2 dash going through the central carbon atom. Similarly, one more. Then we will have sigma planes. One plane containing 4 atoms and the remaining 2 will get exchanged. Similarly, the other one will be like this. These front 2 lobes will get exchanged. Okay, so this is D2T. Now it also has SN. So this is anti-clockwise. S4 means rotation by 90 degree and then perpendicular reflection. So this is a 90-degree rotation, then perpendicular reflection. From both sides, if you do clockwise or anti-clockwise, it does not matter. This is a symmetrical, like all the 4 bonds on the carbon atom are H only, so this is symmetrical. But when you change these 2 atoms, the symmetry point group reduces to C2. We are only left with C2. The planes are gone now because we cannot, sigma planes are gone because we cannot exchange H and Cl anymore. This exchange is not allowed. So the planes are not there. And also the C2 changing this, so we had this C2 is also not there anymore. So this C2 is not there because H and Cl again will change their place. Okay, so this C2 is gone and another C2 this C2 remains because this down H gets exchanged with the top H, but and this C2 also remains. So we have 2 C2s. One this direction, one in perpendicular. So we have 2 C2 excesses left. The point group is C2. Now for C infinity V, you get this kind of for heteronuclear diatomic. Heteronuclear diatomic molecules. Example, HCl. So you have H, C triple bond. Now this lies in a plane. Okay. Then you will have a C infinity axis passing through this plane. So because these atoms are supposed to be considered as spherical, so when you rotate along the plane by any angle, you will get the same configuration. The atom will not change its place. So we have C infinity, and also you have infinite sigma V planes. How? Because since it is spherical, you cut the atoms half by through any plane, be it this plane or this green plane or some angular plane. By any angle you cut it, you will get the same molecule back. So this has infinite sigma planes. So C infinity V is for linear unsymmetrical molecules, CO, HF, Cn minus, NO plus, like that. Now second option is D infinity H. So it is linear unsymmetrical, so dipoles are not getting cancelled. Now D infinity H is for symmetrical molecules. No, it can be triatomic as well for symmetrical. Symmetrical with linear symmetrical with center of inversion. So due to presence of I, their dipoles get cancelled away. So a non-polar molecule can have this. tetrahedral. If it is symmetric, it will be non-polar. But if it is not symmetric, it will have polar. It will be polar. And D option is also same. Octahedral, symmetric, polar, sorry, non-polar. And not symmetric will be polar. Okay. So the question is, a non-polar molecule can never have. So it can never have C infinity V. For ferrocene, upon changing the conformation from staggered to eclipsed, the following symmetry elements is or are lost. Ferrocene look like this, which is eclipsed, and eclipsed has point group of T5H. But if it is staggered, it will look like this, and it has a point group T5D. So in D5H, the symmetry elements are E, C5, S5. So C5, let me write 5C2 after this, 5 sigma V, 5 sigma V along the ring, sigma H passing through the ferrocene Fe atom, and center of inversion. For staggered, we have E, it also has I, C5, 5C2, 5 sigma D, and S10. Has S10. How S10? Because we have to, so it is 5 means 360 by 5. But for S, we have to rotate it in between. So this bond comes here. So we have from here to here we have to rotate. So this will be 360 by 10. Okay, so 36 degrees. But in eclipsed configuration, if we rotate by 36 degree and then reflect, we will not get the same conformation. staggered ferrocene. If we want to show the S10, so this is the S10 passing through, the excess passes to C10 passes through the Fe atom. So it is rotation by 36 and then reflection. So it is there both sides, clockwise, anti-clockwise. But when you see the eclipsed, we don't have S10. Instead, we have S5 because we now have to rotate by 72 degrees and then reflect because the bonds are eclipsed in this case. So just 172-degree rotation will bring one carbon atom over the other from the top ring, and then reflection will take the same to the bottom ring. So the answer to this question is, upon changing the conformation from staggered to eclipse, we lose S10. All other things are intact. Sigma H. Let's see sigma H here. This same plane is sigma H plane. See in the staggered. So we lose sigma H as well. But sigma H is, yeah, we lose sigma H as well. Traces or the character of, trace is sum of diagonal element. Trace or character of a transformation matrix for clockwise and anti-clockwise rotation are. Now, for clockwise and anti-clockwise rotation, the matrices transpose of each other. Now, on doing transpose, the diagonal elements do not change. Hence, their sum, which is the trace or the character, will not change. So, the traces are same, equal to each other. anti-clockwise rotations are the same, because for anti-clockwise rotation it will be transpose, and on doing transpose diagonal element don't get changed. For example, for Cn rotation plus means clockwise along z-axis, the matrix is cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So here trace is 2 cos theta plus 1. Now for anti-clockwise, along z-axis we have cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. Here also trace is 2 cos theta 1, because this diagonal element doesn't get changed on doing transpose. So the answer is A. Transformation matrix for the principal axis of allene using the 4 CH bond as basis cannot be. Now let's name the hydrogen atom as 1 2 3 4. Now this is allene. Point group we just discussed for our question, which is D2D. Therefore principal axis is C2. Now let us consider this C2. What it will do is H2 H1 H4 H3. So it exchanged. So let me write, this is the original basis. Now after transformation, H1 became H2, H2 became H1, H3 became H4, and H4 became H3. Okay. So the transformation matrix will have elements transformation matrix will be looking like, so 1 is getting exchanged to 2. So 1 will become 2, 2 will become 1, 3 will become 4, and 4 will become 3, and rest other elements are 0 because there is no mixing. So now this matrix is given in option A. So A is possible. Now next will be again the principal axis will not change, passing through maximum number of atoms, so C2, but we can definitely change the numbering. So let me write 1, 2, 3, 4. So this will give 1 will get changed to 3, 2 will get changed to 4. So the matrix will be, first will be 0, 0, 1, 2 will get changed to 4, okay, then 3 gets changed to 1, 4 gets changed to 2. So here, so this is also possible. Now this is given in option number B. Now if the numbers are this is 1, this is 2, this is 3, this is 4. So 1 gets exchanged to 4, 2 get exchanged to 3. So the transformation matrix will be 1 gets exchanged to 4, so this will be 0. 2 means second row gets exchanged to 3. 3 gets exchanged to 1, sorry 2, and 4 gets exchanged to 1. So this option is given in C. So this is also possible. But look at the option number D. So it is changing 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this is not possible. There should be change in a pairwise. All of them cannot change their place. We cannot rotate them like this. So D is not possible. There should be pairwise change. We cannot have cyclic change for all of them. So D is not possible. This question is about unitary transformation of a unitary matrix always yields a matrix that is unitary. So this has been discussed earlier. option C is correct.